Hi everyone, my name is Vanshika Singh and I am a third year student pursuing BTech in Engineering Physics at IIT Roorkee. As part of my coursework, today I'll be presenting on the topic Echo Cancellation in Communication Systems. So here we have a general overview. I'll first be talking about what echo is, the types of echoes, why is echo cancellation needed in the first place. We'll talk specifically about the acoustic echo cancellation, its components, procedures. Then we'll also discuss a few adaptive filter algorithms. Then we'll talk about the performance metrics related to echo cancellation and also its applications in other fields. So starting off with understanding what is echo. So echo is a phenomena where a delayed and distorted version of an original sound or an electrical signal is reflected back to the source. Now how is it different from a reverberation? It mainly depends upon the time of arrival. If the second sound is coming like in a very short time as compared to the first one, then our brain interprets it to be as a continuous spectral distortion and hence it is a reverberation. But if the time of arrival has about 10 milliseconds of difference, then we hear it as a distinct sound, as a distinct echo. Talking about the types of echoes, there are mainly two echoes which are relevant to our discussion. First is the acoustic echo and second is the line echo, also known as hybrid echo. So for understanding acoustic echo, let's assume a situation in which a boss is talking to her employees, let's say through video calling. So whatever the person speaks in this microphone gets transmitted and goes out through this loudspeaker, and this signal, this voice signal gets reflected from various surfaces or walls or furniture kept in this room and enters the microphone. Now understand that people sitting in this room are also speaking something. So their speech signals gets mixed with this echoed sound, and the person sitting over here is not able to understand properly what the message actually is. So this is what we talk about is acoustic echo. In line echo, it mainly occurs due to impedance mismatches in this entire telephone circuitry, which connects to about 2 wires or 4 wire systems. Now, why is echo cancellation needed in the first place? As I also talked about in this previous example of video calling, the echo can lead to a lot of unwanted noises, which leads to degradation in the audio quality. It causes delays, and very importantly, it creates confusion for the speaker as well as the listeners. So there is an obstacle, an interference in the communication that takes place. We don't want that to happen. What echo cancellation does is that it improves the clarity and the quality of audio by detecting and then subtracting the reflected signals. It also reduces the feedback loops in the speaker microphone setups, hence enhancing the overall user experience in these modern digital systems. Here is a small demonstration as to why echo cancellation is needed. So in this example, first image, the person talks and the voice gets out from the loudspeaker and it again enters the microphone in this room. Hence, it causes an echo in this phone and the person hears a lot of sounds which is not needed. And with an echo canceller, all these extra sounds, they get removed and hence it leads to better communication. For this discussion, I'll be focusing more on the acoustic echo cancellation. Why is that so? Because in acoustic echoes, the delays are much longer as compared to line echoes. The echo path may also change according to the movement of the microphone. In this, the background noises are much stronger and they are non-stationary because they come from various sources like the walls, the furniture, the people, etc. In this case, there also is a possibility of double talk, wherein both the parties want to speak at the same time. So how do we go about reducing this acoustic echo? This can be done in three ways. The first is by using frequency shifters, also known as phase shifters. So what we do is that we place them in the electrical path of the feedback loop. Each time a signal travels round the feedback loop, it is shifted by a few hertz before being retransmitted by the loudspeaker. This method has some effect in reducing the howling effect, but it is not very useful in the removal of the echo from the acoustic feedback. The second way is by using notch filters. They are useful at a fixed frequency and they are categorized by two parameters, attenuation and the quality factor. So what these notch filters do is that they help in reducing the feedback gain at those specific frequencies where the feedback, where this acoustic feedback energy is concentrated. But the drawback of this method is that in addition to reducing the feedback, these filters also result in the distortion of the desired signal frequencies. Coming on to the third, adaptive feedback cancellation system. It is till now the most effective method. Coming on to the requirements of an AEC, firstly, it should have a fast converging adaptive filter. Secondly, the convergence should be stable. And all this echo cancellation should not lead to any performance degradation for the real speech signal. Now the components, it firstly has an automatic gain control AGC, which is basically an analog to digital converter while receiving, and it acts as a digital to analog converter DAC while sending out the signals. It is followed by a double top detector. Then there is an adaptive filter followed by an NLP, which is non-linear processing. It basically helps in removing the traces of residual echo, specifically from the error signal, followed by a noise reduction and then some comfort noise. Now I'll be discussing the general procedure of an AEC. So this part is the far end setting and this part is the near end setting. The adaptive algorithm plus the circuitry consists of our AEC. Our AEC is made up of these things. Now quickly going through the denotations. XN stands for the far end signal. Whatever is being spoken here goes into XN. Here we have YN, which is basically the echo signal, like whatever is being echoed. And our VN is the near end signal, basically whatever is being spoken into this microphone. So this echoed signal plus the microphone, the signal is essentially becomes the DN, which is the final output from this particular microphone. Now this DN, we subtract the Y hat N from this. Y hat N is the filter input. This gives us En, the error signal. As you can see here in this equation, En equals to Dn minus Y hat N. So this is how the procedure goes. A far end signal is delivered to the acoustic feedback synthesizer. So this far end signal goes into our acoustic feedback. The far end signal is reproduced by the speaker. So this signal is transmitted through this line and it is produced by the loudspeaker in this particular room. The microphone in this room picks up the sound. The far end signal is filtered and delayed. So when the far end signal enters this AAC, it is filtered and it is also delayed. The filtered far end signal is subtracted from the near end signal. So as we can see, the DN is our near end signal. So our far end signal is delayed and subtracted from this, and hence we get En. The resultant signal does not contain any direct or reverberated sound produced by the speaker. The adaptive filter forms the heart of the AC. It is the most important part of an AC and it determines how good the echo can be removed from the near end signal. There are several algorithms that have been tried in various realizations, and each of them have their own benefits and weaknesses. Some of them I'll be discussing here. The first one is the LMS algorithm, the least mean squares. It is the most basic adaptive filtering algorithm, and it adjusts the filter coefficients so as to minimize the echo. It is used in the time domain echo cancellation. Second is the normalized LMS, in which the step size is normalized on the basis of the signal power. It is more effective for echoes in signals with variable amplitude, hence it improves on the convergence speed. It can also be applied in the frequency domain filtering. Third is the recursive least squares algorithm, also known as the decorrelational filtering. It provides a faster convergence by minimizing the least squares error over all the previous samples, but it is computationally expensive, although it handles the correlated signals better. Fourth, subband filtering. In this, the signal is divided into fixed, non-overlapping frequency bands, and then the echo cancellation is applied independently within each band. It improves the accuracy by focusing on specific frequency ranges only. It is simpler and it is more computationally efficient, especially for stationary signals. The fifth is the wavelet-based cancellation. Wavelet-based echo cancellation, it uses the wavelet transforms and decomposes the signals into time frequency resolutions. It helps in enabling a more precise echo removal across the different scales. It is especially important for non-stationary signals. In this presentation, I'll be discussing the most popular and the simplest of the adaptation algorithm, that is the LMS algorithm. It defines the cost function as a mean squared error. It is simple as it does not involve any matrix calculation. It is based on the method of the steepest descent. So in this, we move towards the minimum on the error surface so as to get the minimum gradient. And we do this by estimating at every iteration. I'll be going through a brief derivation so as to better understand the LMS algorithm. So we can start off by modeling our adaptive filter. So we will have the input xn, and for each input value we having filter weights wn, w1, w2, wm, etc. So for getting the output of our filter yn, we are basically taking a dot product of the transpose of the weight vector with that of the input vector. Second, coming on to the error signal en, which is basically the difference between our desired output tn and the filter output yn. We have replaced the value of yn from the first equation here. Now the cost function. So the objective of LMS is to minimize the mean square error. So this becomes our cost function. Here you can see that en was the error signal. We have taken the square of it, and e being the expectation operator. So overall this becomes the mean square error. Now that we have our cost function, we follow the gradient descent rule, which says to minimize the mean square error, the LMS algorithm updates the weights in the direction of the negative gradient of the cost function. So the gradient of our cost function jwn can be approximated as minus 2 enxn. Using this rule, we get the final equation for LMS weight updatation. So the filter coefficients w are updated using this equation, which is wn plus 1 is equal to wn plus mu enxn. Here mu is the step size and it controls the convergence speed as well as the stability of the algorithm. There is a condition on mu for LMS algorithm to become convergent, and the condition is that mu should lie between 0 and 2 upon lambda max. So here we can see an example of echo cancellation working. So the first signal, this is the near end speech signal. Basically, what the person wants to speak in the microphone is this. Now, the second graph is what the microphone actually picks up from the room. Basically, it is what the person wants to speak plus the echoed signals. So, this has a lot of echo in it. The third and the output signal is very similar to the near end speech signal, which means that our echo canceller has successfully removed the echo, and the person in the far end can only hear what the person in the near end wants to speak. There is no echo in the communication. Now I'll be discussing the metrics through which we can judge the performance of our echo cancellers. The first one is the echo return loss ERL. It measures how much of the transmitted signal is reflected back to the echo. So basically a higher ERL would mean a better echo suppression. Echo return loss enhancement ERLE. ERLE quantifies the improvement in signal clarity after the echo cancellation. It is measured in decibels and indicates how much echo is reduced. Its formula is as follows. ERLE equals to 10 log base 10 echo signal power upon the residual echo power after the cancellation. Third, convergence speed. The time taken for the adaptive filter to adjust to the echo part changes. Faster convergence ensures quicker adaptation to dynamic environments. Double talk performance. The ability of the system to correctly handle double talk situations without causing distortion or attenuation of the actual signal. Here are the applications and situations in which echo cancellation comes in very handy. Firstly, telecommunication. Like both the mobile and the landline systems use echo cancellers to improve their call quality. The video conferencing example, like the one I discussed earlier, in which people use Skype, Zoom, Teams, etc. to have a video call, and it requires advanced AEC algorithms to ensure that echoes are suppressed during the real-time communication. Third, automotive communication systems. Like these days, we have a lot of hands-free calling systems within our cars. So in that scenario, it is very important to eliminate echoes because the cabin of the car is really small, and it could the echoes will distort the conversation a lot. Fourthly is in smart devices like Alexa, Google Assistant, etc., which have to detect our voice, and hence there should not be any echo. Otherwise, the instructions, like whatever instructions that we give, they will not be clear. Thank you everyone for viewing my presentation. May you all have a good day.